Good morning, everyone. We are just waiting for Professor Epidemri sir to join. Then we will start the session.
Good morning, sir.
Good morning. Hello, everyone. I can see that Professor Epidemri sir is already joined this session. So I'm requesting sir to please start the session.
Yeah, thank you very much, Saurav. And I'm happy to join again today in continuation with my yesterday's talk. I understand that what we have discussed yesterday have led to certain kind of understanding developed in the context of climate model, mathematical modeling. Of course, there are many ways of understanding climate. Climate model is one of them. So it should not be mistaken that only climate modeling is needed to understand the climate. Yes, climate modeling is necessary if we want to go back in time or we want to go further future in time, because we don't have observation in the past, long past. So we do trading analysis, we do proxy generation data, we run the paleoclimate model. So we fill in the gap with the help of this modeling strategy, and in coming future maybe you have much better strategies, much improved model and much improved mathematical model which is coming in the context what we are discussing today. And then with that comprehension yesterday, and now for further understanding, if we want to go for downscaling per se, what is the downscaling means? Now every model has its own limitation, predictability limit, how accurate, how bad, good, as I yesterday have shown you, demonstrated very accurately that there is a kind of precision needed for the model. There are a kind of tweaking needed in the model, that how good and bad it is. So that's what we have already discussed yesterday. And there is a need of bias correcting model output, or whatever you call it, it's kind of a rehabilitating the bad guy. You correct the things, and there is nothing perfect as such, we know in the nature. So these model are set of equations. As I said, I don't want to go in mathematical detail because I'm told it's a very heterogeneous set of people here. So I will not go in mathematics. So of course, for fundamentally, now I'll touch upon today again what we discussed yesterday. These mathematical models are based on the conservation of mass, conservation of momentum, and conservation of energy. All of us must have read this in our previous classes sometime or another. So I am not talking anything big. So it's a very simple thing which we have already understood in our previous notes, and based on that previous notes that we have kind of improved upon that, how these laws which we studied in our previous classes, how these laws can be implemented for seasonal or regional climate modeling or global climate modeling. Now, when I say climate modeling, it can be at any scale. One is the global climate modeling. So whole the globe we know, and these equations are run at the global climate modeling. So when we are talking of the global climate modeling and at that scale, primarily we are looking on or at the processes which are at global scale. Suppose a cloud burst in Himalayas or anywhere in India, right? It may not be having global scale kind of capture, because at the global scale we may not be able to capture a small mesoscale phenomena which is in tens of within few kilometer, which is occurring at one point location, whereas the global scale it will not be captured. And matter of fact, at global scale we are not interested to see the impact of cloud burst at Mumbai or at Delhi. It doesn't matter much, right? So we are, it's something like you are talking of a flood which come instantaneously on a river, but simultaneously if you have seen ocean, there is a huge front of wave comes. So you must understand the difference at global scale. When we are talking of the climate, we are looking at the much larger scale perspective at spatial as well as the time domain also. Like westerly jet, we want to see how the global planetary westerly jet is going in this context. There can be water budget, there can be global clouding. We want to look global averaging of the temperature, increase or decrease, whatever it is. So that's what is global climate needs to work, and coarser resolution where we are more keen on working on global scale phenomena. Whereas at regional scale phenomena like Indian summer monsoon, tropical cyclone you can add on one, Indian winter monsoon, western disturbances, they are the regional phenomena for at synoptic scale phenomena. That's what we call synoptic scale, that is in hundreds of kilometers. Global scale, as I said, that thousands of kilometer scale phenomena. Synoptic is 100 of kilometer scale phenomena, where in which the Indian summer monsoon comes. I'm talking on the Indian perspective now. And then there is a mesoscale phenomena, that is a tens of kilometers tropical cyclone. Then further down, if we go, we have a micro scale phenomena. It comes cloudburst, hurricane, twister, and then dust devil, whirlwinds. So you have to see that for what purpose we are looking at, what kind of mathematical simulation or models needed for that, right? And in view of that, then we can talk of certain manifestation, we can talk of certain issues, and based on that certain issue we can talk on that. And then we have to keep in mind this philosophy, what we want to do. As I said yesterday also, at times people get confused that you have a model, you can do anything. No, you need to know that what you want to do first. You want to work on Indian summer monsoon, or you want to work on a planetary wave. If you want to work, or even some solar system, then you have to go get out of the planet also. If you want to work on solar flares, or if you want to work in sunspot, even you have to go to much larger scale of planetary solar scale. So based on these kind of philosophy, you have to understand if you are working in agriculture crop system, if you are working on the local flood system, if you are working on the urbanization system, if you are working the local exchange of the fluxes, you have to talk on the regional or mesoscale phenomena, where you cannot use the global scale phenomena, global scale models, because they will be too coarser for utilizing the global scale phenomena in that context. Hence, you have to come down to the regional scale phenomena. Hence, the concept of downscaling, concept of bias correction comes in the picture, which we will be discussing. Now, fundamentally, to understand downscaling, what does that mean? There is a dynamical downscaling, there is a statistical downscaling, right? As since Saurabh has asked me to talk on this, so I'll briefly touch upon that, because they are highly technical, because you need to have certain kind of mathematical methods to understand to downscale. So now in that context, when we are talking about the downscaling, we primarily need to understand what we want to downscale. It means that if that global scale phenomena, we can downscale at regional scale by certain means, it means that we are using the larger scale input for a finer scale output. That's what is our need. If I want to use the global climate model data like CMIP 6 is started coming, CMIP 5 is coming, previously now SIMPs. So they are a global scale phenomena. They may not capture the regional scale phenomena what you and me wanted to learn at. So what is that? In that context, we need to downscale that. So GCM output, we make an input in the regional climate model. It's the dynamical downscaling. Please remember, when I say dynamical downscaling, I am always talking on time, each time step in that equation. Whereas in statistical downscaling, I am not talking in regular time interval. I am fixing the time of today and tomorrow, suppose 24 hours. But what happens in between 24 hours, I do not know. Right? So there is a difference. Whereas in dynamic downscaling, at any time in between 24 hours, also if I want to know, even in the seconds, I can simulate that model. So I'm calculating dynamical downscaling based on time, which is not the case when I am doing with the statistical downscaling. In statistical downscaling, the relation with time is not very well looked. So that is the lacuna of the statistical downscaling. But statistical downscaling is absolutely good at times when it is happening in that scale. So that's what is the basic philosophy of dynamic and regional downscaling. And based on that, we want to say that what is the dynamic downscaling and what is the regional downscaling. So if we understand that dynamical downscaling in the climate model, there are many methods, there are many ways people are talking of the dynamical downscaling. So downscaling is a method for obtaining high resolution climate or climate change information from relatively coarser resolution of global climate model. Typically, global climate model have a resolution of 150 to 300 kilometers by 150 to 300 kilometers in latitude and longitude direction XY and EZ. Many impact models require information at shorter scale of 550 kilometer or less, the way I said regional scale, the way I said the agriculture crop, the way I said the monsoon method. So some method is needed to estimate the smaller scale phenomena. I hope all of you are getting my point that in case of dynamical downscaling, we are using a GCM to be having less resolution. GCM provide information at less resolution, higher resolution, limited area model. So dynamic downscaling uses a regional climate models, or RCM we call it very properly. And this RCM is forced by the boundaries used from the GCM to drive a smaller scale phenomenon. So it can dynamical downscaling is appropriate whenever impact models require small scale data, not the large scale data. However, it has a limitation that it will be only limited to very smaller scale phenomena, and it will have a boundary value problem. And based on the boundary value problem, you will sometime need to correct it, this general name of downscaling, if you want to understand that dynamical downscaling requires running of high resolution regional climate model at subdomain using observational data, lower resolution model data output as a boundary condition. So these again uses the same physical principle to reproduce local climate, but are computationally very intensive. Because why computationally intensive? In GCM, as I said, that we are using coarser resolution of simulation, 150 to 300 kilometer by 300 kilometers means at this much big area you have one point of data to calculate. But when I'm taking the final resolution data, it means that each 50 by 50 kilometer I need one input. So naturally your processors, your computer processors have to work more, and application of such relationship to the output of global climate model to the local climate characteristic is very, very important. So there are various methods. I think you people can go to that dynamical downscaling at regional and climate model. There are many papers which are happening. The philosophy of both the models say GCM runs at the larger scale, RCM at the smaller scale. So this RCM is forced with the GCM. This is the fundamental of dynamical downscaling. Nothing more than that, nothing less than that. So you need not to confuse what is the dynamical downscaling. And briefly touching on the statistical downscaling and the difference between two downscaling are to briefly touch on that is statistical downscaling model is primarily used to downscale the regional climate model at a particular point location where sometimes you feel that a suitable regional climate model is not very capable of doing this, or maybe the statistical downscaling of regional climate for present climate evolution or future climate projection. People also do these two methods of regional climate and dynamical downscaling, on which I will come at subsequent classes, subsequent discourse in my presentation. So I am switching now to my presentation, and based on my presentation, I will can you all see my screen, please?
Yes, sir.
Okay, perfectly fine.
Yes, sir.
Yes,
So
sir.
I'm
Yes, sir.
starting that. If you remember that till now I was talking about. Can you switch off your mics, please? Thank you very much. I'm sorry. So if you look at this figure now at the climate change of Karakoram and Ladakh region, yesterday itself we talked about how complex we are going, how less observation we have, but now we have to study the impact study or Ladakh and Karakoram. So if I want to study that region, we don't have observation. We have a global climate model. So whatever study I'm preparing or making on this aspect of global climate change over Karakoram and Ladakh, I have to be very curious and I have to be very cautious also that if I'm talking based on the models correct or not. Right? Number 1 point. Number 2 point, if I want to be as correct as possible, how can I be? Because in case of global climate model and even regional climate model also, the information whatever is will be given on this region will be at 300 by 300 kilometer in global climate model or 50 by 50 kilometer in regional climate model, even after downscaling. It means that I am kind of using the data which is much at coarser even for these two regions. So I need to have bit cautious using the model data. So I am showing you an experiment, rather our study over the Karakoram and cold arid region, where that there is a need of this purpose of kind of comparison of how the Karakoram and Ladakh region is working, because recently you all must have come to know that in Karakoram people told that there is a glaciers are increasing. And that was the reason I chose this study, why glaciers are increasing. Now this is impact question. I told how for impact you have to use the Karakoram, you have to use the regional climate model. So if you all have certain kind of impact question, now question comes how all of you will in that context will be able to provide the impact analysis. So that's what one example I wanted to bring to your table, so that you understand that it's not that simple that you simply use a global climate model and based on the global climate model, you provide your results. It will be kind of deceptive. And we know that already there is a topography is an issue over this region. And primarily when you are talking of the elevation dependency of precipitation and temperature, at last slide yesterday, if you remember, I have talked about that in monsoon and winter season, because these are the two main seasons where we receive the precipitation. So I chose over these two reasons how the monsoon and precipitation varies with time, varies in vertical elevation when we are going from down to vertical at lower elevation to higher elevation. So as we discussed that there is a positive trend in glacier mass balance has been reported by 2004 by Hewitt. Hewitt told that there is a kind of increased glacier. Everywhere glacier is depleting. All of us know that because of global warming. But Hewitt told that few reasons in the Karakoram so that there is an increase in glacier mass. So it is very intriguing for all of researchers who work on Himalaya. How come glacier mass in Karakoram only increases, whereas rest of the mountainous region in the globe, they are reported to be decreasing. Subsequently, Gardel and many others have also said that it's a heterogeneous spatial pattern. So glacier elevation somewhere is increasing, somewhere is decreasing. And that's why I chose these two regions, Ladakh and Karakoram, which are adjacent to each other. If you look at this first figure here, they are very close to each other. Black boundary is for Karakoram, red boundary in Ladakh. In Ladakh, glaciers are decreasing. In Karakoram, glaciers are increasing. So the region which is so close to each other shows very distinctly different pattern of region. So very fundamentally, I want to say that most of the elevation ranges in Ladakh or cold region receive higher precipitation than Karakoram. Ladakh receives higher because in summertime, moisture from Indian summer monsoon also goes there, and it is kind of sorry, Mahendra Singh, I don't know what you want to request me to do. Mahendra Singh? Mahendra Singh, somebody is there? I don't know what to do. He want me to do something. I don't know if I understood what it means. Anyway, I'll go ahead then. Some message has come from Mahendra Singh. So if it is happening in that way, then we can think how the precipitation when we climb within the Himalaya, when we go within the Himalaya, this Karakoram is changing or not changing. And in view of, okay, I think he wanted me to do this. Okay, right, I got it. Oh, okay. So you see the Himalaya, when you climb up, the precipitation and temperature are not distributed similarly. They are distributed differently, right? So when precipitation and distribution in vertical temperature is differently in monsoon season, and here in the winter time, if you look at that in winter time, then you have a different kind of assessment of physical processes. We must know, as I told, we must know what are the physical processes. If we do not know, then it's problem. And if you are looking at the trend of precipitation in the summertime and in the winter time, you see that in summertime, your precipitation and temperature trend in Karakoram is almost similar. However, in case of colder air, which is in red, as you climb up, your temperature elevation dependent warming, as I was discussing yesterday, in higher side, your temperature is going to the negative. So trend based on this is like this. Whereas in case of the winter season, there is not much change of precipitation trend. In Karakoram, it's almost same. It is not changing, neither decreasing. However, in Ladakh, your change is decreasing in the vertical, right? And in case of temperature, if you look, that higher elevation is colder. Trends are cooling over the Ladakh region more, but the Karakoram's temperature is almost looks like isothermal. There is no change happening in Karakoram as we go up and down. It's something like that. It's keep going, whereas Ladakh is decreasing. So this is the trend based on 30 years. And similarly, if you look at the winter time also in the Ladakh region, which is shown in the red, your temperature is decreasing. However, the temperature is not changing much in Karakoram. So Karakoram, your temperature from lower elevation to higher elevation almost remains same, where in case of the Ladakh region, your temperature is kind of warming in the Ladakh region in higher elevation, whereas the lower elevation is comparatively less warming. Okay. Oh, how to delete it now? I messed up. In case of identity pattern, in case of aridity pattern, if we are looking at last 30s, I hope all of you know what is aridity. And if you look at aridity pattern in last 30 years, we found that lower southern flank of the Himalaya is comparatively more arid as we climb up in the vertical in this pattern, we find that there is a more dry along the foothills of Himalayas. If you are climbing blue color, you are more humid comparatively, but as you go to the higher Himalaya, your dryness is become subhumid or semi-arid, and the trend of aridity is kind of increasing. Or if you look at the second graph here, you look this blue color, your aridity pattern are decreasing, increasing. It's becoming more arid, more humid, whereas in this Ladakh region in last 30 years we see that the aridity patterns are decreasing. So Ladakh is becoming more drier, I mean to say that, as compared to Karakoram. This is the last 35 years we have seen. And if you look at the pattern in higher elevation, if you see that Ladakh is going, the trend of aridity index shows that Ladakh is kind of going negative in the decadal trend, where as the Karakoram is kind of having similar kind of pattern, similar kind of exchanges as we are going vertical up in the free atmosphere. So that's what is the anomaly pattern. And then we try to look at that how and why this kind of aridity, this kind of changes, this kind of pattern changes. What happens to the increase of glacier mass? It means when fundamentally you look at the increase of glacier mass, it means that glacier has to attain the mass from somewhere, and then it should keep it within. So that's what we try to look at, what's happening in the monsoon season and what's happening in the winter season. As I told already, these are the two prominent precipitation yielding phenomena, and based on these yielding phenomena, we found that what happens that LCL, which is the cloud base, we call it LCL, lifting condensation level, where the cloud base, all the cloud, when you see the base of the cloud is where the saturation starts if your air parcel is going. So I'm not going that physical process, I'm just simply limiting it to the LCL, determines that how much of moisture is getting dumped. Until unless there is no moisture, cloud will not form. You have to have moisture where it will be saturated or it will be kind of. And trends in LCL height during summer shows it lowering over the Karakoram. I hope you got it. So LCL, the cloud base which we see in the free atmosphere, it is very close to the Karakoram as compared to Ladakh. And then when it's very close to the Karakoram, whatever the moisture is coming within the Karakoram LCL, it is kind of dumped over the Karakoram, which in case of Ladakh, when the LCL is up here and when the precipitation is falling down, in between there is a lot of atmosphere in which this liquid precipitation is, or solid precipitation in the form of snow, is getting lost. So that is the very critical problem of Karakoram region in winter as well as the summer also. And primarily over Karakoram, we receive more precipitation due to the western disturbances in the winter time. And winter time, already all of us know that is more stable season, and based on that winter time, your LCL, when it's lowering, will enhance the cloudiness. When cloudiness is also increased, even if it's not precipitating, but cloudiness, if it is increasing, it is stopping the incoming solar radiation. It is not letting go to the surface of the Karakoram surfaces, and hence the snow melt or glacier melt will also be comparatively dampened by virtue of the cloud, which I have shown in yesterday, roughly at 3,000 meter height. There is an increase of cloud, and there is because of the increase of the cloud, there is a decrease of downwelling long wave radiation. So this increased cloudiness is associated with moisture. Of course, we have to have a moisture, thus inhibiting the warming, leading to cooling over the atmosphere. So this is not letting the atmosphere, the warming, this inhibiting the incoming solar radiation, and hence the cooling is starting. So this hypothesis we are kind of proposed here in the context of the Karakoram anomaly, and based on that we gave a very preliminary hypothesis based on these four figures. And if you look at look at this graph, and we are moving this way, and we find that if you have a trend of temperature, skin temperature, surface temperature is decreasing over the Karakoram and Ladakh simultaneously. So if temperature is decreasing, skin temperature, definitely it will not help in melting the glacier mass which is available in the free atmosphere. And by virtue of that, if you look at the trend of snow surface in figure B, there is an increased trend of surface snow amount. So snow surface is increasing because the temperature is not there, melting is not happening, warming is not. So whatever the snow is getting over this region, it is getting dumped, and hence the glacier mass is increasing. And corresponding energy fluxes, if you go to the figure C, which is here, figure C, what we see that over limiting to the Ladakh and Karakoram region, we find that trend of surface upwelling shortwave radiation is positive. So most upwelling shortwave radiation is exited from the glacier mass. So if your energy is more exited from the mass, again, you are losing energy to the adjacent atmosphere. By virtue of this losing energy to the adjacent atmosphere, you have less amount of energy needed for melting. So you have less amount of energy, and hence again, melting is reduced over the region of the Karakoram. And in case of long wave radiation, if you look at that, the trends are negative. It means that long wave incoming radiation, upwelling radiation trends are negative. So that leads to all cooling over the Karakoram region. So that's kind of a snow albedo feedback based on the model physics we try to provide. If you look at this all snow albedo feedback is provided based on the remote climate model. So what I want to emphasize upon, any process which you are trying to define, any process which you are trying to exaggerate upon, you need to have a kind of physical process understanding primarily prior to the framing of the modeling strategy, because at the modeling strategy you need to know what kind of processes you will be doing in the context of whatever you want to do over the region or whatever you want to carry forward over the region. So this is what we use model for. The crux of our discussion is how we are using model from GCM to RCM to physical process at very regional scale. Right? I will come to the point scale also, where this regional downscaling will also not work. I'll get to that subsequently with few of my papers where you can understand what I mean to say that. Similarly, over Indus Basin, if you know, all of you must be knowing the Indus Basin. Indus is a very famous river that cuts across the northern part of Indian states, Ladakh and JNK, and moves to the adjacent country, Pakistan. And in that, what we try to see that in trend in 1970 to 1999, 100 years, 130 years surface air temperature. If you look at different RCPs, I don't want to again go into what are the RCPs. I assume all of you know what RCP is, and these all four panels are for winter, March, April, May, June, July, August, September, and October, November. So you know 4 seasons, and they are at different RCP, RCP 2.6, RCP 8.5. So based on that, what we are finding that the increasing trend of temperature average seems to be much higher in the month of October, November, but not in JJAS. In both the RCP, if you look very carefully, your temperatures trends are increasing. In JJAS, as I told yesterday also, there is an increase of moisture happening in this, and by virtue of increase in moisture, what's happening is the case of this increase of moisture is not happening by virtue of availability of moisture. The temperature is damp. Temperature is kind of lost within the temperature dampening masses. And the lower slide, if you look at the lower panel of these slides, you distinctly see that there is a kind of decreased temperature. Somebody else is handling my screen. Mahendra, can you stop annotating here, please? Who is Mahendra Singh? Saurabh?
Yes, sir. Yes, sir.
Who is Mahendra Singh is annotating on my screen? Is the guy from outside?
Somebody? I think, sir. We'll just remove him.
Somebody is sharing my screen.
Sir, can you reshare it, sir?
So there is no participant Mahendra Singh here of this name.
Sir, can you just reshare your screen, sir? I think Mahendra was there, sir. I just removed him.
Who is this guy?
Maybe, sir, he's a student.
So why he is annotating on my screen then? Can you see now my screen again?
Yes, sir. Yes, sir.
So this one is increased precipitation pattern here, which is going up in the different RCPs, right? And based on different RCPs, if we are trying, so anybody can access my screen. That's what I mean. Understand that, Saurabh?
Yes, sir. Your screen is visible, sir.
No. But how somebody can access apart from?
Uh, I don't know, sir. Actually, we have never tried to note any screen right now. So
No,
this was a new experience for us also.
this is a good inquisitive question. Actually, we should
Yes, sir.
like RCM Codex. This thing we should also. Anyway, we should invite Mahendra Singh to that maybe. So
Okay.
it's good for presenter. Anyway, getting back to that. So all of you can see here there is a distinct increase in temperature on Indus Basin, and based on this distinct increase of temperature in Indus Basin, of course they are not homogeneously introduced over this region, but they will be kind of some seasons are warmer, some seasons are less warmer, but mostly all the seasons are warming. So if this warming happens, how will be the impact? So anyone you working on impact, please think of this, how this impact is happening. And coming back to the precipitation, if you look at that, somewhere interestingly over the Indus Basin, you have a red color wherever you are seeing. There is increased precipitation we have noticed. This is very inquisitive how that increased precipitation in the model physics is happening. Right. So if there is increased precipitation, it means there are the mechanism where the precipitation is coming here from somewhere. But in particular, you look the October, November, which is the last season. October, November is mostly dry season, like spring and autumn we call it, or fall we call it, right? But the precipitation is increasing in particular these two seasons. It means that there is certain mechanism will work over these regions based on which the precipitation is likely to be increasing or improving upon, and that's what is the case. Water storage, which is the key impact. You look at that water storage. If you look at the particular total precipitation minus evaporation minus runoff, the water storage, if you look at over these regions, you will find that in particular in the C figure, June, July, August, September, JJAS, over the monsoon time, it will be kind of increasing, that the precipitation is likely increasing in the upper Indus Basin, but the lower riparian of the Indus Basin, it has a deficit of precipitation happening. If there is a deficit of precipitation happening or increase of precipitation is happening or so and so forth, then there will be huge impact will occur in the lower riparian of the Indus Basin as compared to the upper riparian of the Indus Basin. And trends are also indicating that in increasing time, the precipitation is likely to be improving over this region, and the hydrological budget when we are talking, so water storage is going to be increasing, in particular the higher upper riparian of the Indus Basin, whereas the lower riparian of the Indus Basin is likely to be depleted with the water. Coming to the climate change over Kashmir Valley, I am showing you the segment of a smaller region now, downscaled for a smaller and smaller region out of these. So Kashmir Valley, what does it happen? You have an all-around increase of maximum mean temperature. If you look at this Kashmir Valley, the black dots are dots where kind of increasing temperature is reported in last 30 years of data. So based on the last 30 years of data from 1980 to 2014, we found that there is a kind of distinct increase of precipitation are happening in the floodplains, in the flood foothills, in the mountain, in the Karawas, whatever it is the Kashmir Valley, because it's a very peculiar valley. You have a kind of valley coming in between, cutting northeast to northwest to northeast direction, and hence it's important to precipitation is decreasing, of course, in all the places in the higher rim of the valley. The precipitation is decreasing all across, and a spatial distribution of precipitation trends over Kashmir Valley is seen in last 34 years. Entire region shows a decreasing trend in the precipitation. Entire region in general, if you look at the overview, you saw that their precipitation is decreasing based on the modeling strategies. But a significant and consistent decrease in annual precipitation of roughly 0.8 millimeter per year. It's a kind of a very alarming. If this model is correctly perfect up to that level, then I will say it's at alarming level. And the precipitation trend at different topographic zone in Kashmir varies, but on an average, I am telling the 0.8 millimeter per day. Coming to the Satluj River Basin, I found that I think Saurabh has worked on the Satluj, right, Saurabh?
No, sir. Actually, I work for Tawa.
Tawang.
Tawa, sir. No, Hoshangabad.
Okay.
It's in Ahmedabad.
So in Satluj River Basin, I found that in next 100 years time, the temperature is increasing in all the RCPs, 2.6, 4.5. Of course, RCP 8.5 is likely to be more increase of the global temperature as we know in IPCC protocol. But in case of RCP 8.5, we have an increase of temperature more than the corresponding pessimistic emissions RCP 2.6, RCP 4.5. So that's what is kind of a variation in temperature. We have seen that temperature is increasing, but it's very peculiar that in case of precipitation in the Satluj Valley, we don't see much change, neither decrease nor increase, and it is very perfectly matching with the present IMD observation also. So when we see this kind of a comparison among various valleys, we find that at some of the valleys model simulate very perfect this thing, whereas the monsoon and temperature and mean surface temperature, particularly I deal with these two important variables. There can be more impact studies, of course, someone can think of. In this, we found that in case of Remo model, which I chose here, that there is not much changes happening in precipitation. Right. Whereas in another valleys, we found there is a distinctly decrease in precipitation is happening, except the Karakoram, which I have already shown you, where increase of precipitation is happening. Climate change of the Ganga Basin, Upper Ganga Basin, it's a more complex in the sense that you have a winter monsoon is also coming, summer monsoon is also coming over these regions, and hence your Upper Ganga Basin project, the projection is kind of a very complex to comprehend at the moment. So we are still working on that different RCPs, what's happening in the Upper Ganga Basin projections. So these are the interim conclusion with the first slide, which I have shown on the downscaling, the temperatures, snow feedback mechanism and impacts you have to take care when you are talking, and particularly this slide is very important for all of you, that impact and adaptation across range of scenarios. Now we are talking 1.5 degree, 2 degree, 4 degree warming, reliability of projection, improvement in spatial and temporal coverage of observation, topographic complexity and its publications. So these all things you have to take into the mind. Method is one, your objective is one, and physical process is one. So when you are talking of the mathematical models per se, GCM or RCM or even the statistical model, you have to be very careful when you are talking of the methods and modeling in this case. So I'm coming to the bias correction. I hope everybody can see this bias correction method. And based on the bias correction, there are various methods of bias correction you can work at. I will not go in mathematical detail here because, but anybody can refer this paper if you want, right? So there are various bias correction methods which we adopt. One is the scaling, and that's a very simple scaling. Linear scaling. Many times you divide point by 1/2, and then you divide by half. You say that's average. One is the geometrical average. One is the mathematical average. Right? So in bias correction, if you are at the horizontal surface, we can divide by 2. It's easy for me. But when we are in the climb or mountain like cascading mountains like Himalaya, we need to have scaling properly done. We simply cannot divide by 2. So the corrected value need to be compared with the observation, and based on this observation for a particular month, because monsoon you have more precipitation, In March, you have less precipitation. So month also becomes very, very important, and day also typically becomes very important, because we need to know what is the temperature of that particular day and what is the, so whenever you need a bias correction, when you want to correct the model output, you need to have a corresponding in situ observation also, and based on that you can employ the scaling method, you can employ the empirical quantile mapping, you can employ the power transformation, you can employ the local intensity scaling. So these are the 4 methods which we have, and based on these 4 methods, we will say that what are the advantage or disadvantage of these methods. If you look at this graph of bias correction, you have advantage of mean based, monthly mean adjustment factor, and various disadvantages also. It's very important to talk of the advantage and disadvantage before going ahead. And based on these, if you have some correction mechanism for temporal distribution of daily precipitation occurrences, so how these 3 models in empirical quantile mapping or the local intensity scaling, power transformation, you can adopt. I'll not go in mathematical details. Please go through the respective publication and papers, and then when you see this IMD one, and this is the uncorrected one, and based on the IMD and uncorrected one, you can have this kind of understanding where you can have this features that if you have this IMD here, you have this uncorrected one model is showing you more amount of precipitation here as compared to this observation. So how based on this scaling, you can use these 4 methods, and based on these 4 methods, you can talk of the improvement in different methods. And based on this methods of correction, you can think of which method is providing you better kind of understanding and better kind of results. So if we have this kind of methods understood, and this is the basically temperature, I think one is the JJS mean temperature, IMD, and B is the but their bias is model minus observation. So that also you can correct. So that's what I wanted to highlight here, that based on the model and based on the data, how can you highlight this kind of improved bias correction methods. So that's what is one I wanted to show here. And based on these factors, you can always kind of work on the model. You can always kind of divide of the model, and based on that, when you're talking of this, you can use this method, and any of the method will be of good use for bias correction methods. Similarly, you have various for temperature you can use for, and now you can see this how this kind of scattering and observation you can compare with. If you look at this comparison of the IMD precipitation uncorrected one and the corrected one, you can see the changes. The first figure is precipitation of IMD when there is a lot of bias in the model, and based on employing the IMD precipitation, you can see that there is a kind of probably improved correction with the in situ observation. So similarly, you can have various kind of bias correction methods. Similarly, I come to one point location. This I have shown at the regional scale, but now here I am showing in the second graph, I am showing at these stations. You can see this map. There are various methods here, and based on these stations, we kind of have many in situ observation. Based on this in situ observation, we are trying to work on these in situ observation, and that's few results I'll show that how it works to have these information done and bias correction is done. I hope all of you are understanding what I mean by bias correction. So we took 2 basins here. Based on 2 basins, these are the stations we have chosen, 9 stations in Upper Ganga Basin, and similarly we have chosen 8 stations in the Satluj River Basin, and we employed the bias correction using one of the method which I have discussed in my previous paper, that how the distribution probability function, cumulative distribution probability function we have used here for precipitation bias correction. And similarly, we have used a distributed quantile mapping for temperature bias correction. And based on that, what I want to show finally that how our results improve. So this figure which I am showing here, it shows that your quantile distribution of precipitation field over these 8 stations or 10 stations over the Upper Ganga Basin, Josimat and all those basin. And if you look at the red line, red dots, these red dots corresponds to the deviation in the model from the observations. If you also look at the scatter plot. So what we tried to do, we bias corrected these red dots based on the in situ observation. We took a point location. At point location, we have observation. At that observation, we have kind of in situ observation, and then we corrected our model observation at that point location. And at that point location, then we have improved upon the correction of the in situ observation. And based on that, if you look at the blue line, the corrected line, and that blue line observation is improved because they are falling very diagonally to each other, and that's what we have done. We have also shown the probability distribution function. If you look at this probability distribution function, you can distinctly see that how the probability distribution function, which is at the green color, are deviating from its mean. As we are going from one station to another station, there are 10 stations in the Satluj River Basin. We have shown here that how the probability distribution function, their mean and spread is kind of improved upon. So these are the few facts I wanted to share with you. Probably I don't want to make it more complex. There is a lot of mathematics are needed. However, I would like to, and this is the graph for air analysis, box whisker plot. Most of you might have heard of how the error analysis can be done. And then this is the final scatter plot of model temperature field before and after bias corrected. So before and after bias corrected, if you look at that, the model temperature and the observed temperature, how good and bad it is kind of scattered. There are two black one, and then bias corrected is blue one. And then we try to show that how close they are, observation and model. So this is the final few things I wanted to share with you. And based on that, if we have anything asked to me, please go ahead. I'll be happy to answer. Unfortunately, I have 11 o'clock. I have my class. We are running three parallel semester. So please go ahead if anybody has any question. Saurabh, is anybody has any question?
Participants, if you have any questions, you can just write in the chat box also, or you can unmute yourself and you just talk to sir.
Sir, am I audible, sir?
Yes, please go ahead. I'm happy. Yes.
Yeah, sir, just actually I am Ajit Naik working for
Sir, am I audible, sir?
Management.
Let him ask. He is asking already.
Yes, sir.
Yeah, please go ahead.
Sir, actually I am working on a project where I'm predicting stream flow using the RCM, climatological variables in Mahanadi River Basin. So, sir, out of Codex SS, so many RCMs are there. How do I choose the best 3 or best 4 RCM, or I have to run everything for precipitation and temperature to find what predict best the stream flow?
I think you have to use all the RCMs. You did not run the RCM. You have to correct the data of all the RCM individually, right? And based on that RCM, you have to tell us that, look, I have used these many RCM and this is the best RCM work for your purpose. That will be very important contribution.
Yes, sir.
How I will know that which will be the best RCM for your objective. You know, so you have to use these RCMs yourself, and based on that, then you have to yourself decide upon that which RCM is good for you, and you have to tell others based on your research that, look, for this purpose, this RCM is better. I hope you got my point.
Yes, sir, just one small thing here. Because last time when I was giving presentation to someone, they told that 11 RCMs. I am choosing some 6 or 7. The question is, how did you select the 6 out of 11? That is the question, sir. I'm not able to
No,
answer
no,
properly.
you can't do that. You have to take 6. If you have availability of 6, you use 6 only. But you cannot say how to choose out of 11 which 6 you have. It's availability that you got only 6.
Okay, fine.
Right?
Okay.
Or else you can do what are the best RCM for the purpose we are reported by somebody, and then you come to the downscale.
Review. Okay.
Okay. Dr. Mamta Dharkar, please, you raise the hand. Dr. Mamta, please go ahead. Somebody raised hand, I can see. Anybody else, by the way? Saurabh, is there anybody?
I
Unmute
think,
my.
sir, there is nobody now, sir. Nobody is raising questions also in chat box too. So
Okay.
thank you very much, sir. You have given time to us and you covered broader aspect of climate models and their different aspects. And we are looking forward for your future expertise in upcoming sessions also, sir.
Sure, Saurabh. Thank you for giving me this opportunity to talk with the. I wish I would have known them, their background much better, so it would have made my job also easier to learn from them also. I thank you all, and I wish you all success in your endeavors. And hopefully, we will be in touch with the email. And Saurabh, again, thank you to you for giving me this opportunity. Thank you and bye.
Thank you very much, sir. Thank you all the participants. We are closing the session now.